So, so what do we know about? So it's a Markov chain. So do we for each realization of the environment? So we have a law of large numbers. It's not that difficult to see that. It's basically the velocity is 0 because we are reversible, so there is no drift basically, right? And we also have a central limit theorem, a Quenched central limit theorem, has been proved by Siderovicius and Snitman using Kipnis-Vardhan theory in dimension 4 and higher, and in all dimensions it's been simultaneously proved by Berger-Biskup and Mathieu Piatnitsky. Okay. Okay. So what about large deviations? So can you say something about for each realization P naught almost every P naught? Maybe I should write it down. So P naught is going to be the measure that we are always going to talk about, and under the assumptions we have imposed, this probability is strictly positive, so it's all okay what we are talking about. Okay, so under this quenched measure now, for each realization of this noise of the random environment, so we are going to say that xn over n roughly look like x, and xa, let's say, bit out from 0 because 0 is the velocity. So can we study the deviations of this, and whether we have a formula for the rate function? Okay, must say, so it's not that difficult to show this statement if you did not care about a variational formula for this. Okay, so there's a subadditivity argument. It's a 5-line argument that shows that this statement is true in all the percolation models, and this rate function is nothing but the dual of the Legendre transform of the quenched Lyapunov exponent. But you really, as soon as you use subadditivity, you lose all information on the rate function. Okay, so it's easy to prove that there is a large deviation principle, but you don't know what the rate function is at all. Okay, so that's what we want to show, and actually we'll prove something else, which will this statement about the LDP will drop out from that. So basically, what we'll not be talking about the random walk itself. We'll just be we'll riff the random walk to the space of environments. So this basically means that I'm looking at tau xn of omega. So now it becomes a Markov chain on the environment space omega 0. Okay. And we'll work with this process. So basically what it means is that we keep track of, let's say we look at a step size of n, and we keep track of the environment process, tau xa of omega, xk of omega, and the corresponding steps. Okay? So somehow it's the local time of the random walk until time n, so the empirical distribution. And I'll show you in a second. So what we are going to show is, so this is a random probability measure on the space of environments times the steps. And I'll show you in a second that if you prove LDP for this, LDP for xn over n, which is the classical level 1 LDP, will follow immediately from that. Okay. And it's not just because we like abstraction, because here the rate function that we get has a very nice entropy structure, and this is something, this is helpful. Okay, so before I go into this story, let me just make a few remarks about literature regarding random large deviations for random walks in a random environment. So one-dimensional case was studied by Graven and Frank-den-Hollander long time ago. I think it was 94 or something like that. So they got some very nice rate functions. And then around 2000, it was Comets, Gantard, and Zaytouni, one dimension, I think also uniformly elliptic, using different methods. So the first one was using branching processes, and the second one is about passage times, using different methods. They also proved annealed quenched, and they had a nice relation between the annealed and the quenched rate function. Martin Cerner in 1999 looked at multi-dimensional random walk in random environment, but the story is quite different there. He also has some moment condition for that, and he used subadditivity. It goes along the lines of Snitman's enlargement of obstacles. And however, there is a formula for the rate function, as I said, because if you use subadditivity, it's a very nice argument, but you lose information. Okay, Vardhan also studied multidimensional random walk in a random environment in a stationary ergodic setup. and drops something, a very technical assumption imposed by Tsana called the nestling assumption, uniform elliptic as well, but he also used subadditivity, but in a more direct way. There was no formula for this. And a couple of years later, there's a very, very nice method developed by Kaushik, Reza Khanlu, and Vardhan in the context of a diffusion in the continuum, diffusion in a random drift, elliptic diffusion in a random drift, and it goes parallel to a homogenization question for Hamilton-Bellman equations. Okay, and this is a very nice approach. It gets a formula for the rate function, and somehow our methods are philosophically close to what they have done. And adapting their methods, there was a PhD student in Grant, Rosenbluth. So in the discrete case, he got in the level 1, he got level 1 rate function for random walks in a random environment in the multidimensional, assuming that the logarithm of the transition probabilities has d plus epsilon moment. Okay, this was extended by Yilmaz. He did level 2, also assumes logarithm of pi has the same moment, as did Yilmaz. So these guys assumes something very similar to this in the context in the continuum. And if you translate it to the discrete case, it just boils down to these conditions. Okay, and using the same assumptions, there was Firas, Rasulaka, and Sepalainen extended to a level 3. Again, log pi has to have the same moment assumption. Okay. There's another approach of Pierre Lyons and Souganidis, and also there's a lot of work of Armstrong and Tran. So it has related results, but somehow they also resort to subadditivity, and somehow it's related to Schnittmann's method. Okay. All right. So this is a short survey. So we are basically now talking about deviation. So note that there is no moment condition here, because we have 0 transition probability, so the log could be minus infinity right away. Okay. Somehow we'll, as I said, as a guiding philosophy, we'll follow this KRV theory. But there are some two main difficulties, as one always has in percolation cases. So first of all, there is ellipticity, always there when you talk about percolation. There's a more fundamental problem here, which is non-stationarity. Okay, so this is of a much more serious problem, as you will see, because note that we are not working with the original measure p, we are working with p0. So we are conditioning on the 0 being in the infinite cluster. Okay, so you have no longer p0 is no longer this tau x invariant. All right. So basically, we want to develop a method, somehow keeping this theory for mind. Somehow it's a unified approach that works in the elliptic as well. It works in the percolation case and also makes the life in the elliptic case, which has been studied a little easier. Okay. Good. So I'm done with the slides. So can I cannot just push it? No. Okay. Okay. So right. So let's look at what we have been. So basically the object is this local times is given by delta tau xk of omega. So this is the environment process. It's a process which takes values in the space of environments. Okay, minus the steps. Okay, so this is a probability measure. This is the space of probability measures on omega 0, and omega 0 is just this event. Okay. What we want to show is that for p naught almost every omega, we want to show that this p pi omega 0, you remember that was the quenched probability distribution, just the renormalized weights basically. So ln looks like a given measure mu in, okay? This behaves like exponential minus n I of mu, okay? So to make it precise, Ln has to be in an open set around mu. It gives you a lower bound, it's a closed set, an upper bound, and so on. But it's a large deviation workshop, so I'm assuming everybody knows about the definition of LDP. Okay, so there is a reason why we are studying this, and let me just make a quick remark on how, if we have this, how can you get a rate function? How can you get an LDP for just the classical xn over n? Okay, so this is very almost immediate, because so let's say you have a probability measure mu here. So mu has two arguments, omega and e. Okay, so now if you take the average of this and integrate it out, you basically get a vector. Okay, so this vector is in RD, and this is basically the contraction map. Okay, so take any mu in M1 omega 0 to u and map it to this this f of mu, which is just so it's like, if you have a sum of delta functions, right, and it's n, this is a measure, you just integrate this measure with respect to the function x. This is, you just get back x1 plus x2 plus xn over n. Okay, so this, if now mu is just for ln, then f mu is just xn minus x0 over n. Okay, so if I have the rate function here, then I know that p pi omega 0 xn over n looks like x, goes like x minus n, let's say j of x, and j of x is nothing but inf I of mu, such that x equal to f of mu. Okay, so that's the contraction principle. Okay, so anyway, so let's come back to this. And what we are after is this statement, and not only that, we want a formula for I of mu. Okay, so right, so as we have seen a couple of times, more than a couple of times actually in this workshop. So this statement is equivalent to showing that some logarithmic moment generating function exists. So n f integrated with respect to ln, that this is equal to some number which I call h bar of f. So if I have that, then I of mu is going to be the Legendre transform of h bar of f. Okay, so let's just try to prove this. This is equivalent. Are there any questions? Okay, so let's start with this. Okay, so we'll prove this in 3 steps. We'll show that there is a lower bound. Okay, we'll show that there is an upper bound, and we'll show that the lower bound is equal to the upper bound. Okay, I'm not saying something very non-trivial, but this is what we are going to do. Okay, so let's look at the lower bound. Okay? It's always the easier thing to do, if you have some experience. So what is the lower bound? So as probably most of you know, so in order to do any large deviation lower bound, you basically have to tilt. So this is your measure, okay? You have to tilt the original measure to something where you can tilt with, again, to pi, but then you have not really tilted, because then there's nothing really which is done. So, okay, so let's look at pi omega 0 of the same object here. And now I want to look at some other transition kernel, not the same one, pi tilde omega 0, and I have done something here, and now I will do this. So whatever I have done here, I have undone here. Okay? But there are a million probability transition kernels where I can tilt. So where do I want to tilt? Again, an intuition in large deviation tells you that you are going to tilt somewhere where you can apply the ergodic theorem. So where can you apply the ergodic theorem? So of course, again, you can tilt at pi because you know that starting from something reversible, you are always going to get an ergodic theorem because it's reversible. There is an invariant measure there. But then again, it's a trivial tilt. You didn't really do anything. So you're not going to get a good large deviation. So where can I tilt? That's the question. So let's look at those pi tilde. So let's first tell pi tilde to be the set of all transition kernels, omega e, so that it's measurable and it sums up to 1, and it's non-negative, of course. But the important condition in percolation case is that sometimes pi is 0, and I don't really, somehow I have to be careful with this condition here. So I that theta is 0 if and only if pi is also 0. Okay? So if the original transition probability was 0, so the new transition probability is also going to be 0. Okay? That's not enough because there is a, I said that you're going to tilt somewhere where the ergodic theorem is going to be available, and we have to classify those transition kernels where the ergodic theorem is available. And there is a very classical theorem in the elliptic case at least, but it goes back to Papanikolaou and Varadhan, and also parallelly Kozlov. It's sort of somehow the holy grail of homogenization, in my opinion, whenever you work with the environment process. So the theorem says the following. So theorem, in the form that I'm going to state, did not appear before because of this percolation issues, but basically it's not that difficult to get it from the original. So fix pi tilde in pi tilde. Okay. So if Q is a measure on the environment space, which is absolutely continuous with respect to pi 0, with p0, and more importantly, or equally importantly, Q is pi tilde invariant. So that means I have a Markov chain being driven by this pi tilde transition kernels, and if Q is an invariant measure for this, then Q must be ergodic. And there exists at most one such Q. Okay, so if such a Q exists, it has to be necessarily unique. Okay, so so basically, which the ergodic ones are basically the ones which are, so then Q must be ergodic, and in fact Q is equivalent to P0. I must also add that. So the ergodic ones are basically the ones which have a density with respect to the original environment measure, and it has to be invariant. Okay, so let's classify those ones. Let's write E to be the class of those transitions kernel pi tilde, and let's say some density phi, such that, okay, so phi is a density, so phi is non-negative, phi integrates to 1, and phi dp0, which is the Q, is pi tilde invariant. Okay? So now I'm going to choose, I'm going to start from here, and I'm going to tilt at a pi tilde such that pi tilde finds a phi which satisfies these assumptions. Okay? You could ask, can you guarantee that such a thing existed? I could, I'm going to assume that it exists, and if it does not exist, I'm going to show you that it didn't cost you anything. Okay? So let's assume for a second that such a thing existed, and then, so now of course I have a 1 over n log here, 1 over n log there, and then, so there's a log here, I can do a Jensen, okay? And then after I did Jensen, 1 over n and n will kill each other, and the log and the x will be cancelled, okay? And since I know I tilted at an invariant pair, therefore I tilted at an ergodic pair, and therefore I'm entitled to use Birkhoff, okay? And if I did all that, limit after n to infinity, it's going to go to integral dp0 phi of omega summation over e pi tilde omega e f of omega e minus entropic cost log d pi tilde, log pi tilde omega e over pi omega 0 e. It might be complicated, really it's not. It's just Birkhoff, okay? But of course, which phi and which pi tilde, I don't know, okay? So I assumed that there exists something. So in order to do the best tilt, I'm going to take a supremum over the class of such pi tilde and phi. Of course, this class could be empty, but then I'm taking supremum over an empty set. This is minus infinity. I'm interested in a lower bound, so that's okay. All right, so this is basically, let's give it a name. Let's call it h bar of f. Okay. And I'm going to start with this variational formula. This is our lower bound. And now I'm going to give a sequence of lower bounds, ending up with some variational formula, which will be our upper bound. Okay? So then I have shown that the lower bound is larger than or equal to the upper bound, so therefore we have proved the theorem. Okay? All right, so first step is, it looks quite complicated because I really don't know much about this class of things. So first step is to decouple this class, this pairs. Okay, so how can I decouple? So let's look at the definition of invariance. Okay, so phi comma pi tilde is an invariant pair. Then I know that every test function g integral dp0 phi summation over e pi tilde omega e g minus its shift, so the gradient of g, this has to be 0 for every test function, every bounded measurable function. Okay? And if it's not, then I'm going to find some test function such that it's not equal to 0. Right? That's the definition of invariance. Therefore, if I take infimum over a class of all bounded measurable functions, I'm going to find a dichotomy. It's 0 if phi comma pi tilde is in E, and it's equal to minus infinity if it's not in E. Why minus infinity? Because if for some g is not equal to 0, I can take constant multiples of that, so therefore I get to minus infinity. Okay? Therefore, here I can simply say decouple this, because I can write sup phi, sup pi tilde, but now I have to do this Lagrange multiplication over g, and this dp0 phi pi tilde, whatever was there before, f minus the entropy. Now I have to look at the gradient, I have to add the gradient of this. Okay? Because if I do the infimum, because it's minus infinity, I don't lose anything if it's not invariant pair. Okay? What do I have? I have a sup, I have a sup, I have an inf. What do you want to do? Minmax. You have to justify first how can we change this sup and the inf. So there are 25 versions of Minmax theorem, which says that if something is convex in one variable, upper semi-continuous in that variable and concave in the other and lower semi-continuous, and if there is some compactness in one of the variables, then I can do min-max. I have, let's assume, and it's really true, that I have all the continuity and the convexity and concavity in the right variables. I don't have compactness, right? Because there is really nothing that tells me that something is compact. But I claim that I have compactness. We just have to look at it. So let's give this functional a name. Let's call it script f of pi tilde and g. Okay? Now, what do I want to do? Let's clean things up a little bit. So f, this is basically integral dp0 phi pi tilde of f plus log pi, because of it's in the denominator, plus g minus its shift. Okay? And then there is some other term which is coming in a second. And all these terms I can bound. This is bounded by C because G is bounded, F is bound, continuous bounded. This adds up to 1 and phi integrates to 1. So this is bounded by C. Okay. Important term is what's coming next is this minus log pi tilde. So this is basically dp0 phi summation of pi tilde and logarithm of pi tilde omega e. Okay? Let's define a measure mu, which is given by phi omega. So phi is fixed. See, we are not messing with phi. Phi is fixed. So this part of the min-max is not yet touched upon. So this phi is here. So this is fixed. Pi tilde omega e log pi tilde of this. So this is a probability measure because if I sum it over E and integrate over dp0, I just get 1. So this is a probability measure. And what I have here is nothing but the entropy of mu. Okay? So entropy, we know that, okay, so again, let's not worry about lower upper semi-continuity and stuff like that. All that really matters here is that it has compact level sets, so, sub-level sets in the weak topology. Okay, it's a very basic thing. I'm carrying a negative sign here, so I'm getting compact super-level sets for this functional in the G in the pi tilde variable. Okay, so if you're believing me with the statement of lower and upper semi-continuity, I'm perfectly entitled to use min-max now. And see that I did not lose anything here in this. So this is a perfect equality that I can carry. So I can do inf G and sup pi tilde. Okay. So now I have an expectation, I have a supremum inside, but I can push this supremum inside the expectation because it's a local function in pi tilde. Okay. So let's do that. Okay, sorry. Sup pi tilde, and now this is an explicit variational problem that you can solve in pi tilde. Okay, so if you do the Lagrange multiplier, so still I'm carrying an equality. I say it's sup phi inf G. I forget what it is. It's logarithm of sum over E pi omega 0 e to the f plus the gradient of G. Okay. So now you have chosen tilt, so to say, the tilt that you have started with, you have chosen it after this Lagrange multiplier computation. We are not yet done. Again, we have a sup phi and inf G. Again, we need a min-max. Again, there is convexity, convectivity, and continuity. Let's assume we really have it. Again, we don't really have compactness. And really, we cannot really do anything here, like before. But, now we are interested only in a lower bound. We want to show that the lower bound is larger than or equal to the upper bound. So we can do this, and we can do generalization with respect to the entropy of phi. What is this entropy of phi? It's basically integral dp0 phi log phi. This is always non-negative because phi dp is a probability measure, so I can do this. Okay. I really don't want to do that. That's why I put epsilon. Later, I will just send epsilon to 0. Okay. Okay. So let's. Okay. So I forgot this integral phi dp here. So now let's push this integral inside, and again, basically there's some things to check here, but essentially it's this argument again that you have to use. You have to exploit that because you subtracted this entropy term. Again, you have coercivity here. You have compact superlevel sets. Therefore, you can use min-max. Okay, and again, if after you use min-max. So again, you can do inf G and sup phi, and this functional is again something that you can maximize over Okay, so again you have to do a Lagrange multiplier, and basically what you end up with is inf g epsilon log e to the 1 over epsilon of this functional there, this logarithm of, so let me call it LGF. Okay. Now, basically, what do we want to do? We can, for any, since there is infimum over G here, so now we can get a sequence of epsilon n's and a sequence of GNs such that this is bounded above by this, where did it go? This H bar of F. That's where we came from, right? So, so the upshot is that it's a sequence of F going to 0 and a sequence of, we don't really know anything about it, sequence of bounded measurable functions Gn such that this H bar of F dominates epsilon n log e to the 1 over epsilon n of L Gn comma F. Okay, and if I now define capital Gn of omega e to be the gradient of small gn, conditional on the fact that 0 is in the infinite cluster and conditional on the fact that the edge 0 to e is present, okay, then it is just a formal gradient, not yet a real gradient. I mean, it is a gradient, but it depends on n. You can show this Gns is bounded in LP, and you can take a weak limit so this Gns converge weakly to G, and G satisfies very, very nice properties. Okay, so G is in a class, let's call it script G, and let's assume what properties this limiting G has. So first of all, it's already clear that Gn is a gradient because that's how I have defined it. Okay, so Gn is a gradient means that I can define. So G is also going to be a gradient weakly. So that means I have a closed loop property. Means that if I take a start at 0, let's say x0, take a path in the cluster and end with xn, which is again at the ending at the starting point. Now if I sum over that path, then about this closed loop, the sum is 0. Okay, so this means that I can define what I call a corrector v omega x as a path integral, and the path, choice of the path doesn't really matter, from 0 to x. Okay, and this, the choice of the path x1, x2, xn minus 1 doesn't really matter because I have a closed loop property. Okay, so this is an important feature of this. What's the next one? So the next one too is that G, very strong statement I'm going to make, G is bounded. So why is that? It's because of, where did I write it? Okay, so there's a statement which, so H bar of F is larger than or equal to this. That's what I just wrote before, right? So you can show that basically since let's not spend too much time on that, but let me say just one line here. So note that, I know that sometimes these transition probabilities are 0. So these are potentially dangerous, okay? But now the structure of our effective Hamiltonian, or whatever you want to call it, is such that even if I'm 0, I don't cost anything to the Hamiltonian. So basically, I only have to look at the edge which is present. And if it's present, it's larger than or equal to 1 over 2D. Okay? So one upshot is that essentially your random walk behaves as if you were uniformly elliptic. Okay? So that's all that depends on in showing that G is bounded. Okay? There are things to do here, but that's what it really. And the third thing that I would is that G would have to be mean 0. Okay? So if I look at this, I could say, of course, G could it's a gradient, so why is it not mean 0 right away? It's not, again, because of this problem that I just mentioned before, because under the E0, the P0 measure, this is not, the tau E are not preserved, the shifts. Okay? So this definition doesn't really make sense. So we have to somehow, so this is called an induced mean 0 property. It's a little technical. So this how much time do I have? Okay, so I'll very quick. So let me not spend any time. So there is a notion of induced shift and induced mean 0 property that it's a little technical to define it, but you can do it. Let me just finish with the 2 lines regarding the upper bound. It's very easy actually. So I told you that we started with the lower bound, which is this. And we showed that the lower bound is larger than or equal to this object in there, where this inf over G essential supremum. Okay, so I didn't say anything about the essential supremum, but it's very easy to see because epsilon n as it goes to 0, I have epsilon n log e to the 1 over epsilon n of this. So as epsilon n goes to 0, it basically converges to the essential supremum. Okay, so h bar of f is larger than or equal to this. Okay, and this infimum of G is over infimum of capital G, and capital G is now in this class of functions, this capital G infinity, which has closed loop, which is bounded, and which satisfies some mean 0 condition. Okay, and this is basically our upper bound. Why? It's very easy to see. So now note that what do we want to show? We want to show that this n f of ln, okay, if you write down what ln is, it's basically f tau xj of omega tau xj plus 1 minus xj. Okay, so I want to estimate this. Okay, I want to estimate, perturb it. I will take a g from this class, and I will do a character perturbation, so to say. Okay, so I will do the same. I'll just put the same variables in G, and I will estimate this. Okay, so how can we do that? So let's forget about the sum. So if I condition on, let's say, one of the variables here, then this is nothing but sum over E. Transition probability is pi, so pi omega. You go from xj to xj plus E, and this is now to the omega xj plus E, and the same with G. Okay? So now this is just a number which is, for each G, this is bounded by this, because it's an essential supremum. Okay? So this, if I call it lambda, fg for each fixed G, so this is less than or equal to e to the lambda fg. Now I wanted to do the sum, j from 0 to n minus 1 or something like this. So forget about the conditioning. Now it becomes a product, and if I do successive conditioning and the Markov property, what I basically get is e to the n times this. Okay? So if I take 1 over n log of this, I'm just ending with upper bound that I just promised. However, now I have also the corrector terms that I have perturbed with. And now one of the main steps now is to show that the perturbation that I have caused here didn't cost me anything. So basically what you have to show is that these correctors that you have defined via the closed loop property satisfies so the theorem that has limit n to infinity 1 over n sup x is less than or equal to n, v omega x equal to 0 almost. The corrector only has a sublinear growth at infinity. So if you do that, you can simply forget about this term because this perturbation is really negligible. And therefore you end up with the upper bound. Okay? So this is basically the formula for the effective Hamiltonian or the h bar of f that I just promised. And if you take the dual of this, this becomes the rate function that you are after. Okay.
What can you say about the properties of the rate function?
Nothing.
Well,
so we know that it's convex. It's for a general random walk in a random environment in higher dimension. I mean, okay, I guess we're not talking about one dimension.
No. But higher dimension.
Higher dimension, it's for a general random walk. So forget about percolation clustering, and let's say dimension 2, let's say your uniformly elliptic random conductance model, you really know nothing about this. You don't know where it has flat pieces, and I'm thinking about it, but it's.
But in that case you would think that there would be no flat pieces in higher dimension. But then that
okay,
is still,
let's ask this question. So we know that in dimension 4 and higher, the quenched and the annealed rate function are the same. Okay, but if it is ballistic, okay. So if it has some direction, it has a directional transience, the condition T is satisfied, then the result of Attila-Yilmaz, which says that it's the same. And in dimension 2 and 3, there is a slight problem that it has. I keep forgetting. So it agrees on a neighborhood of the zero set, and it does not agree on that. So I would expect that So let's say we are reversible, so there is no ballisticity. I don't even know whether it's really true that the rate function agrees in dimension 4 and higher. Because Yilmaz result, we thought about it for a while, and Yilmaz result really needs the condition T. Otherwise, it completely collapses. Otherwise.
And are there other things that you can get like that the rate function is larger than the one for the homogeneous simple random walk, so by some convexity property? Because this is another property that we know in one dimension, that the rate function is strictly larger than the one.
No, really, no. So other than very trivial use of Jensen's inequality, which tells you that this is larger than or equal to that, and it's not only me. I mean, I talked to Varadan, and it's a very difficult question. But there is some this entropy structure in the variational formula that was missing before. So this is something which came new, and hopefully it will lead to something which is non-trivial.